So this lecture is going to be a brief introduction to strain. What is strain? And maybe the best way to think about it is look at what we've done so far. So up until this point in the course, we've really focused on forces and stress. So if we've got stress, is really just if we really boil it down, it's just a force divided by an area. Now, for strain, is really so stresses are innately related to forces. Now, strain is going to be related to deformations. So, the really the definition of a strain is just going to be the change of a length over the original length. And we give strain this, and so we'll write this out a little bit more mathematically. So strain, we give the Greek letter epsilon, and it's really just going to be delta over L. And so if we have say we take a small, uh, bar here, and we pull it, well, it has some original length L, and then we extend it by some distance delta. Well, that's just our strain, is this delta over L. One thing to note with strain, so with stresses, we've got the same units as pressure, so a force over area, so newtons over millimeters squared. But strain, well, because it's change in length, so say this delta, well, that'll be in millimeters over our original length, which is millimeters. And this really means that strain, well, these cancel out, right? So strain is unitless, and often it is reported as a percentage. So as percent, which makes sense. So if you're going to strain something by 10%, that means you're going to stretch it 10% longer than its original length. So that makes a bit of sense. So I've drawn a little demo here, but I've got a little demonstration here. So I've got this this sort of rubber band here. And well, what we want to do is go through and strain it. So I'm going to put a mark for this is going to be our original length L. And what we're going to do is we're going to strain it some distance delta, and that looks like that's approximately I think I could fit about 5 of those in there. So this is a strain of approximately 20%. And that's kind of, we'll grab this and pull and try to do it so it still looks good on camera. There we go. You get the general sense there. Well, we'll grab that and pull. So, you've strained it, you've pulled it. But a big thing to note with strain is that it's really dependent upon what this original length is. So we can get the same strain with a smaller deformation. So say I grab, or if we go to the same deformation or same endpoint from a smaller perspective, you can see, man, there's a lot more stretch going on. There's a lot more strain in this rubber band than if I'm grabbing just right here at the end and pulling. So strain is really dependent upon this original length. This becomes a huge deal. So I'll just in concrete buildings. So, strain is dependent on and so we'll just give you a little preview into your third year. This is a really big deal in concrete buildings. And the reason it's a big deal is if you crack over many cracks, you can spread your strain demand out. Well, if you crack over one big crack for the same deformation, you'll get a lot higher strain in your reinforcement. But like I said, that's maybe for outside of this course. The big thing to remember is that your strain is all dependent upon that original length. So we'll just draw a little diagram. This is really just what I just showed you with the rubber band, where if we pull to the same total distance, say we pull to here, so this is our original, and then this is our delta. And obviously this is either a very stretchy material, or it's a very exaggerated case. But we'll call this L1 and L2. So strain in L1 is going to be simply, we'll call that delta 1, and delta 2 is going to be delta 1 over L1. Huge delta, small l, strain's going to go up. Now if we have strain 2, it's just going to be delta 2 over L2. And again, you're going to have a much smaller strain. So strain 2 is going to be less than strain 1 because this deformation is going to be much smaller by pulling all of this to the same point. So we have a much larger deformation here on delta 1. We could see a similar behavior if we keep the deltas the same. So say we have this, so here we had two different deformations, but we pulled, everything to the same overall displacement. And this is really what happens in concrete buildings. This is, say, one big crack and a big deformation. And this is, lots of little cracks. And so any given crack is a smaller bit. But as I said, I'll refrain from going too far down that tangent. But say that we have, again, our same L1 and L2. But instead of having different deformations delta, say we've got the same length. So this, delta 1 equals delta 2. So these two are the same. So strain 1 equals delta over L1, and strain 2 equals delta over L2. Well, if L1 is less than L2, then the strain in and our first bar here is going to be much higher. Strain 1 is going to be greater than strain 2 because we're pulling it a higher percentage of the total length. So we are straining it more. And again, that just comes back down to what our definition of strain is, where it's a percentage. It's a percentage of stretch. So that's our general overview for what strain is. Now we talked a lot about strain, a lot about stress, but what's our relationship between these two? Well, what we'll do is we'll use the example of a steel bar. So we'll look at relationship between stress and strain. So imagine we have a steel bar, and it's a circular bar. And we're going to pull it in tension. Well, what we want to do is, as we're pulling it, well, we're going to measure both the force and the displacement, and we'll plot this up. And this is kind of what the force displacement if we pull a steel bar in tension looks like. So first, we'll pull it. And as we pull, we apply more force. We have this nice sort of linear behavior until we reach the yield capacity of the steel bar, and it yields. And once it yields, well, the molecules rearrange, and it can't take any additional force. And so it yields, and we get this this flatness. And so it's this point here we'll call Fy, and so that's our F-axis, and this is our delta axis. And there's a corresponding delta Y. So this is our what we call our elastic limit. So our elastic limit, which is our yield line. It's also sometimes called the proportional limit. Because you can see, because we're linear, we have a nice proportion between F and delta. So for a given displacement, we know that we're going to have an increase in force. But after this, we yield. Now let's say before we go too far, as we load up and down this section, well, our material, if we unload it, it comes back to zero. It comes back to its original piece. And so I've got this this binder clip portion. So this guy here. If we flex it, it arrives back to zero. It's here in this elastic limit. So I'm going to take this this piece off here, and it's doing much the same. So if I hold it here, I can sit and I can flex it, and I can flick it like that, and you see it will deflect, and it will come back. And so that's the material property. However, there'll be some portion, if I bend it too much, you see it's wider than it was. Well, I've yielded it, so the material won't come back to zero. And in fact, if I unload, I will unload down at the same sort of stiffness K, which we will find out soon, this stiffness K has a really important property. Well, if I keep loading this, at some point, I'll start increasing load again. So let's give some of these, points on our graph some little numbers. So number 1 is our yield point. So any load or displacement below this point and when released, it'll come back to 0. But after we've yielded, say we come to point 2 here, this is what's called our yield plateau. So this is our plastic response. And if we unload, we're going to get a residual displacement. So that's what happened with this binder clip. We'll bring out the other side where you can see kind of, well, this is what it started as, but then I pulled it much further than it started at. I basically pulled it past yield. And then when I unloaded it, you can see it's got a residual deformation left. So it's landed somewhere here, and I could have pulled it here, and it'll unload and unload. And it unloads at the same rate as the elastic loading. And that's true for anywhere up here. All right. But like I said, if I kept pulling on this guy, and I measured the force, well, at some point, it's actually going to start to increase our load. And all the way up to some peak. To some ultimate force. And this point 3 is what's called our strain hardening region. Strain hardening. You sometimes might hear it referred to as work hardened. And what's occurring in this area is that the steel molecules are actually rearranging themselves. And through that rearrangement, they can actually take greater load. And we'll go all the way up to some ultimate displacement. But then we find that the material actually starts necking down, where it's you pull it far enough, you see it gets thinner here in the middle. So as you pull it, it stretches out like if you've ever seen saltwater taffy. It's doing the same thing. And this region is our necking region. And it'll go all the way until it fractures at 5. And that fracture point is our ultimate displacement. And so, some interesting thing to note, our ultimate displacement and our ultimate force don't necessarily line up, particularly for steel, which is what we call a ductile material. So the only thing that's going to line up is our Fy and our delta y. That's why there are a proportional limit. This is why this is a really special point, and because any loads below this level, when we unload it, we return back to zero deformation. So that's our elastic design. Anything up here is plastic, and so for a lot of for our limit state design, we're designing right on this level of plasticity. And then we allow for, we've got all of this extra deformation capacity, which we hold in reserve in case we have a bigger load than we expect. We also have additional force capacity, again, because we want to deal with uncertainty in our structures. We don't want to have this come down on someone's head and hurt somebody. So that's why we can account for all of these buffers. So again, so we looked at forces and displacements, but what does this have to do with stress and strain? Well, our force, to go to a stress, we just divide by an area, and strain, we just divide by that delta over the original length. So, well, let's just redraw this, but instead of, F and delta, let's redraw it with sigma equals F over A, and epsilon equals delta over L. And there'll be, some L, and that'll be some area A. So if we redraw that, we'll see because these are just proportional, we really have the same shape. So you'll have your sigma, epsilon. You'll come up here and you'll fracture at some point. Sigma alt, sigma y, sorry, epsilon. So yield strain, ultimate strain, yield stress, ultimate stress. And keep in mind that these relationships that we have here are what's called engineering stress and strain. And we'll explain that here briefly, but it's I'll show you really quick. It's mostly because of what's called Poisson's ratio. It's that, see, as I stretch this, not only does it get longer, but it also gets skinnier. And for engineering stress and strain, we assume that getting skinnier part doesn't really happen, particularly for anything down in the elastic section. So this is ring stress and strain. So what's also interesting to note is that we've worked a lot with stresses. So like we design with forces and stresses, but it's really strain which causes damage. And so we can look at our stress strain distribution. We can kind of see that. So all of our designs are working really kind of staying below our yield stress. Even if we get plastic deformation, we've got a substantial amount of strain which we can go through. And even if we pull past this, we see that we don't actually go up to a much bigger force, but it's really this stretching, which is what will end up finally breaking a specimen or a structure or a piece. So you can, if you've ever done this with a paperclip, you've sat and you bent a paperclip back and forth. You didn't really take a lot of force to do that. Area hasn't changed, so your stress hasn't changed, but you did have to go through really big deformations, and that's because it's steel and you have a really large strain capacity. Similar sort of thing if you take a piece of chalk. Chalk doesn't have a lot of strain capacity, so you can snap a piece of chalk or snap a matchstick and it doesn't deform a lot. So it doesn't have a lot of strain capacity, so it fails quickly. So it's really strain, which is what's causing all of these, any damage in a structure. Yeah. So the next thing we want to look at is this. Relationship between stress and strain is the slope of our proportional line here, and we call that E. So if our a slope of a line, so if you have got E equals rise over run, that's just going to be sigma over epsilon, our stress over strain. Well, if we rearrange this, what we see is that sigma equals E times epsilon. This has a special name. This is called Hooke's law from Robert Hooke. In sort of same time as Newton, and he discovered this using springs, where it's this proportional constant for a given force down, you would get a certain elongation, and that was true for many materials, and it's so true that we've found this in relationship and given it this name. But also this big value E, this sort of slope of this line, has a special name. This is called the modulus of elasticity, also known as Young's modulus. And this really tells you something about the stiffness of the material. I mean, if a stiffness is just how much force it takes to move something a certain distance, well, we can see that for engineering stress, engineering strain, it's a direct proportion to our force displacement. This value K here equals E. So our force displacement is also going to go up at the modulus of elasticity of steel. And you get different moduli of elasticity for different materials. So steel is approximately 200 gigapascal. Concrete is about 1/10 that. Aluminium is somewhere in between the two. And so for steel, if it has a E equal to 200 GPa, well, if we want to find out what our yield strain is, so say we know what our yield stress is, so as we've pulled a material and we've snapped it, well, I've told you that, deformation is really what causes damage. Well, at what strain do we start plastically deforming the material? So we can work that. So say we've got, for a, so what is the yield strain for grade 300 steel? So for grade 300, Fy equal to sigma y equals 300 MPa. That's given. That's just sort of by definition. And E equals 200 GPa. Well, we can use Hooke's law, and we can go 300 MPa equals 200,000 MPa times our yield strain, and we can work that out. Our yield strain equals 0.0015, and that means that's the same as 0.15%. So that's kind of crazy if you think about it. So if you've got a 100 millimeter long piece of steel rod, and you pull it and you manage to increase its length by less than a millimeter, by 0.15 of a millimeter, you are going to yield the steel. So there's not a lot of movement. And so every time we draw our stress strain curves like this, this really isn't to scale. It's well, if this is going to be 0.0015, our ultimate strain on steel are something about 0.2 to 0.25, so about 20 to 25%. So for that same bar of steel, in order to rupture it, you've got to increase its length by 20 millimeters. While just to yield it, you didn't have to pull it that far. It's a fair amount of force in order to do that, but it's not a lot of deformation. So that's and that's why I say that the strains are really related to damage rather than forces. Let's talk briefly about this engineering strain and Poisson's ratio. So as I said, these relationships here, we were assuming that the cross section never changed. Not really until the necking portion, but as we load up through here, as we're pulling on it, we didn't assume that like if we've got our rubber band, you can see the rubber band gets skinnier. You can see where I've grabbed it at the ends, which was the original size. In the middle, it's getting skinnier, so it's straining in both directions. For engineering strain, we ignore the ones where it's getting thinner in the middle. And for most of our applications, that's perfectly fine. But that relationship between those two is called Poisson's ratio. And Poisson's ratio is just, we call it, this, Greek, I think this is nu. And that's just the lateral strain divided by the longitudinal strain. So for for a given original piece which we're pulling, well, the ends will stay about the same, but they'll sort of bend in. Well, you've got some strain here, and you've got some, we'll call this delta lat, delta long. It's going to be the difference between this width, so this deformation divided by this width, and this deformation divided by the original length. And like I said, you can see it really clearly in our piece of rubber here, where as we pull it, it gets much skinnier. And then if I increase the strain, you can really see it coming down. Rubber has a Poisson's ratio of about 0.5, so it will move. It will have about half of the strain laterally that it does longitudinally. So say rubber nu equals 0.5. For steel, Poisson's ratio should be between 0.2 to 0.3. All right, so that's Poisson's ratio, and that's, as I said, we ignore that for longitudinal strain, but it is an important concept. But it's, like I say, it's not terribly difficult to wrap your head around. It's just how skinny something gets for when you pull it. So the last two things that I want to talk about are the difference in material type. So ductile versus brittle. So for these two, what I'm going to do is just draw two stress-strain behaviors, one for steel and one for concrete. So, in fact, I won't even do stress-strain. I'll do force displacement. So for steel, we've drawn this a few times now. So we have the ultimate displacement, and we have the yield displacement, Fy, and F ultimate. So, and then if I draw a concrete force displacement, so this is our steel, this is our bar in tension. Concrete, think of this as a cylinder of concrete in compression. So our concrete is going to look something. So if this is our delta, and that's our force, our concrete is going to come up really high force, and the force displacement looks a bit like a lollipop, where there's not really a true yield, but we'll do our best. And then you've got the delta alt. So let's just take a quick pause and talk about what's our difference here. So for our steel, I mean, if we look at our sort of relative differences between our yield and our ultimate forces, they don't look too terribly different. But where our really big differences come in is when we look at our deformations. So for steel, look at the difference between our ultimate displacement and our yield displacement. versus concrete, our ultimate displacement is really close to the yield. So think about concrete. Just think about it like your piece of chalk, where it doesn't take a lot of deformation to snap a piece of chalk. But in order to, say, break a paperclip, you've got to really bend it around. You can bend it 180 degrees back on itself, and it still won't break on you. And this is the difference between a ductile material and a brittle material. And ductility is how we measure really how much deformation a material or a structural element can take while still supporting load without breaking. So ductile So ductility, and we give it the symbol mu. So this is the ability to deform past yield and still support load. And it's a really simple equation. So mu equals the ultimate displacement divided by the yield displacement. So steel is very ductile. Well, at least like this is the shape of like a grade 300 steel I have. Higher strength steels have less ductility because they have a little bit more of this lollipop shape. But you'll learn more about that next semester when you talk about materials. So we can do it either with deformation or we can look at strain. So if we look at the strain ductility of steel, well, that equals, we determined that our ultimate, I said, was, about 0.2 to 0.25, and our yield strain was 0.0015. So we have, that's going to be, equals mu, that's going to be 0.2 divided by 0.0015. That equals 133. That's a massive number. That means that we can, after we've yielded our piece of steel, we can continue to extend it 133 times what that deformation and yield was. It's massive. And so we like ductile behavior because it gives us a lot of, say, warning. So you think about a paperclip. You can bend a paperclip a lot and say that paperclip was supporting a load. You'd get a lot of deformation before the thing snapped. And so you could see, there was a problem. It's also good for, say, earthquakes where, an element's going to get cycled back and forth, a whole bunch. Well, we can limit sort of the forces going in. We can just let it yield. But then if it can chew up all of that deformation as the earthquake keeps going on, well, that's a really good behavior for us. So we like ductile materials and ductile behavior. That's lots of formation capacity and gives a warning before failing. Now, if we contrast that with our concrete, which is concrete's a brittle material. We tend to find, some similar behaviors in brittle materials, at least those used in construction, is they tend to have, relatively high strength and small deformations. But the big one is there's a really sudden failure. After reaching peak load. So, you can see in concrete, we get peak load, and then pretty soon after that, we start losing capacity. Well, if that peak load was still trying to get supported, it's going to really, we're going to lose all load carrying capacity immediately. You can think about a piece of chalk. Push on a piece of chalk, and then it just snaps. Well, and it snaps all of a sudden. So this is why we tend not to like brittle materials. Or, in the case of concrete, what we do is we put reinforcing steel in there so that we can transfer any of the load of that concrete in tension as it broke into the steel, and let the steel do all of the deforming job. I guess the final thing and so that's sort of, ductile and brittle materials. The last thing to sort of note is that you can also have sort of loading characteristics can be ductile and brittle. So we tend to like flexure tends to be on the ductile side, and shear tends to be more brittle. Now there are some exceptions to these, but in general thinking, we like flexure. We like things bending. If you design your specimen right, you use the right materials and you use them in the right way, you can get beams to sort of bend like literal bananas, and still be able to support load. While with shear, because there's not a lot of deformation in shear, we can load, and then all of a sudden the material just lets go. And so shear is a far more brittle behavior than flexure. And so this is why when you continue on with your understanding and your education in structures, you'll find that when we're doing our design, we tend to penalize our shear capacities a lot more, and it's really to try to avoid this brittle failure. And we want to make sure that things fail in flexure, that they're nice and ductile, and that gives us lots of really good understanding of how this structure is going to behave, and it gives us all of this warning in case we sort of have more load go in than we expected. So that's our brief overview of strain, and then sort of the difference between ductile and brittle materials and ductile and brittle behavior. And so that's going to wrap up this module. So thank you very much.